Hey everybody, I'm Jason Lupoi, editor-in-chief of Terpenes and Testing Magazine and Extraction Magazine. And today I wanted to tell you all a story regarding how the notorious CO2 became a superhero. So throughout my life, I've had the opportunity to look at CO2 from two very distinct, very polarizing vantage points. On the one hand, I was doing research for renewable energy applications, and I was looking at different types of botanical plants for downstream purposes in biofuels or bio-based materials, the usage of which could allow us to supplant our dependency on the burning of fossil fuels, which creates CO2 in our environment. But on the other hand, I started to learn a lot more about the cannabis industry, the hemp industry, and I started getting involved in botanical extraction. And I started to learn all the ways that CO2 can be captured from these industrial processes and repurposed here on terrestrial Earth. So this is CO2's story. Before I begin, I just wanted to thank some of my colleagues at Thar Process for providing the data that you'll see here today from some of our processes. I wanted to thank Celeste Miranda, as always, and the Mace Media Group family for providing me with this opportunity to share this data with you. And of course, I wanted to thank all of you as well for tuning in today. So I've got good news and I've got bad news, and I like to get the bad news out of the way first. So you all know this already. We have a CO2 problem here on Earth. You've seen smokestacks like this ejecting debris, particulate gases into our atmosphere. And, this is something that's quite known from industrial processes. Like I said a minute ago, the burning of fossil fuels definitely creates carbon dioxide in our environment. And you can see this on the left-hand side of the screen with the graph titled Global Temperature and CO2. So here you can see this trend line of the average temperature going from 1880 up to 2013. You can see that there's definitely some ups and downs there, but by and large, the overall trend over the last several decades has been upwards. And the average CO2 levels in our atmosphere have also trended with this rise in temperature. There's downstream ramifications from this, such as oceanic acidification. You can see this process schematically on the bottom right of the screen, where you see atmospheric carbon dioxide dissolving in the ocean, creating carbonic acid. It ionizes, you get hydrogen ions, that then increases the pH of the water, so it's more acidic. And this has ramifications such you see here, it's the deformation of shells. So this is something that's definitely disruptive to Earth's ecosystem. But the good news is that while we still must continue our efforts to quell these emissions, we can capture this waste CO2 and we can repurpose it for greater good. So CO2 is an ostracized but very cheap gas. It can be captured from industrial processes like the burning of fossil fuels or the forging of iron and steel. And these industries, they don't want this CO2, which is why they're able to sell it off cheaply. And it can be used for creating things like low carbon liquid fuels or as a building block in chemical syntheses. But more relevant to our conversation here today is the fact that carbon dioxide can be manipulated with its temperature and its pressure, which can cause carbon dioxide to migrate into the supercritical phase, where it behaves as both a gas and a liquid. And you can see this graphed on the right in this phase diagram that I've included here, where you see the critical point at about 73 atmospheres and at about 31 degrees Celsius. So above that, from a temperature and pressure perspective, we're in the supercritical phase where CO2 is both a gas and a liquid. And I added the ideal gas law here such that you can see this relationship of pressure and temperature. As one goes up, so does the other, and you can use that relationship to change the solvation power of the CO2, so how well it can dissolve specific analytes of interest. So I wanted to talk a little bit about supercritical CO2 extraction first before we get into some CO2 chromatography. So this is a prime example of where CO2 has gone from this notion of gaseous villain to superhero, and it's a green extraction and purification technique. So everybody in our audience today likely knows that supercritical CO2 is a common way for extracting cannabis sativa. You can see this beautiful plant there in the center of my screen. But it's also been used for a variety of other botanical plants. And at the top left, there's an example of green coffee. You can see some beautiful hop cones on the bottom left. There's astaxanthin, an antioxidant antioxidant on the top right, and you can see God's mushroom on the bottom right, a medicinal mushroom that's been extracted using supercritical CO2. But there's many different types of supercritical CO2 extraction and applications, and I just wanted to list some of these here because I think they're pretty interesting. So you could extract soils and marine sediments, so you can pull out hydrocarbons that are contaminating those soils and marine sediments, and you can thereby quantify how much what the level of the contamination actually was. You can use CO2 to extract alcohol from water. You can extract polycyclic aromatic hydrocarbons from plastic waste, thereby enabling that plastic to be properly recycled. CO2 has been used for deodorizing fish oil, deodorizing low-grade beverages. It's been used for decaffeinating coffee and tea, where it's been said to preferentially remove the caffeine while leaving precious, delicate flavor molecules intact. It's been used for the defatting of nuts and potato chips. So perhaps you've seen these nut powders, like a peanut powder, used as a protein source, but just having all the fat removed from it first. Again, it's been used for extracting antioxidants and omega fatty acids from algae or crustacean byproducts from the seafood industry. And again, it's been used for extracting things from hops and medicinal mushrooms, and of course, Queen sativa. As far we extracted palm oil for tocopherols, which is a source of vitamin E. So you can see my feed, extract, and raffinate samples there. And I wanted to show you guys some analytics too, because these analytics are powered by SFC, supercritical fluid chromatography. So you can use the CO2 in a supercritical state to do the extraction. You can also measure the analytes of interest. In this case, again, the tocopherols and the tocotrienols. You can measure, just like you would in HPLC, for example, you can use the supercritical CO2 to measure your analytics. And this has the benefit of being able to get rid of the use of organic solvents like methanol or acetonitrile that require some level of remediation and require, effective safety controls to be in place. We've also done a case study where we have extracted turmeric, common spice nowadays, and you can see again here the feed, the extract in the center, and the raffinate after extraction. We were again using supercritical fluid chromatography analytically to evaluate our curcumin levels. We've used supercritical CO2 to extract DHA from algae. You can see the feed and a variety of different raffinates here. We wanted to compare our strategies for extraction to traditional strategies such as using ethanol or acetone and also hexane. And you can see from our yields on the right-hand side that we were able to extract as much, if not more, using CO2 versus acetone and ethanol, and while we were about 1% or 1.5% lower in the CO2 extraction yield versus hexane, then you would have to weigh this. Do you want to use hexane in your process, or do you want to use a greener option with supercritical CO2? Okay, so that's enough about extraction. I want to get to the meat of this presentation here, which is supercritical CO2 chromatography. So before I begin, I just wanted to state that this is a way for purifying things like a hemp extract, for example. This is preparatory chromatography. We talked about analytical chromatography where you're measuring analytes, and this is preparatory chromatography where you're trying to purify something. And there's a variety of ways that you can do this. So you may have heard about flash chromatography or centrifugal partition chromatography. These techniques are known for, especially with flash being a more of a quick and dirty method. It's often used as a first pass to be able to purify something. It's important to note that the solvent costs can be pretty costly here, which affects your operating costs. And also that affects your scalability, because if you're trying to purify a lot of something, you would then need to recognize whether you can store all of that solvent on your site, or what kind of safety controls you're going to need to put in place to be able to store large quantities of solvent. So, while these techniques may be a bit cheaper, especially with flash chromatography, they don't quite have the efficiencies and the purification capabilities as techniques like HPLC or SFC. And even with HPLC, often, just like analytically, you might be using solvents like methanol or some type of organic solvent. And so supercritical fluid chromatography gives you an opportunity to do things in a greener, more environmentally sound way. But it is important to note that the equipment can be more expensive on the front side. So it's ideal to look at what your costs are going to be over time instead of just, at the point of sale. What is your return on investment going to be if you're using these techniques for several years, for example? So at FAR, we use a variety of different stationary phases, and just like when you're doing analytical chromatography, these different stationary phases have different chemistries, and that allows us to kind of hone in on different types of analytes. And so we have our the most inexpensive media called Isolator X, and this is best used if you have cost-sensitive research and development going on. For one of our common applications is cannabinoid separation. So being that we're extracting hemp, there's a strong need for THC remediation in the hemp industry, and so we use that type of stationary phase for that application to isolate THC out of a matrix and also to separate out minor cannabinoids for further concentration. And we've got two other stationary phases too that we can employ. They vary in their chemistry and they vary in their cost. So I just wanted to show an example of what one of these systems looks like. So you can see these three different components here. I just wanted to point out the center piece, the longest piece vertically with the black column at the top. That's the column that we're flowing our extract into, or whatever the product is we're trying to purify. We're flowing that into that column, it's interacting with the stationary phase, and then it's being pumped into the larger platform that you see on the right. And really, the main thing I wanted you to see here is we have these four vertically oriented columns, stainless steel columns, that we then separate out our different fractions into. So we can basically collect four different things with these platforms. So usually we say there's three things you can separate, and you have one of these columns for your waste. And so basically what we can do with this is just like in regular chromatography, analytical chromatography, you're separating things out based on their time spent interacting with the stationary phase. That's the same concept here. And when we know when something elutes or comes out of its interactions with the column and is being flushed into the system, when that time frame occurs, we can send that fraction to one of these different separators. And then when we're done collecting, CBD, for example, let's say, in that first separator on the far left of the main platform here, then we can perhaps send THC and minor cannabinoids to fractions 2 and fractions 3. And I'll talk a little bit about that in a few slides. So with this is a smaller throughput system. This is essentially up to 4 kgs per day, depending on how you're using the system, how many shifts, what your flow rates are, things of that nature. And it's worth pointing out as well that this type of technology is not just suited for cannabis, extraction laboratories or what have you. It's been used in preclinical trials. It's been used to purify ingredients for clinical trials, such that you have larger stockpiles of the material, but yet in a very pure fashion. And it's been used for something called chiral separation. So this is when you have mirror image molecules, same structure, just reversed, just like your own mirror image. These can be harder to separate with different types of separation technology, but supercritical fluid chromatography is very well suited for that type of application. And prior to, doing things like THC remediation, that was one of the more common ways to use this type of technology. We also have a higher throughput system, so this is definitely amenable to scale. So this system, again, depending on how you're using it, could process up to 80 kgs of material per day. So I wanted to talk a little bit about some of these applications in a bit more detail. So for THC remediation, we were starting here with a distillate. THC content was, about 4.6%. And so, this is what we needed to try to remediate. Now, this is an example of analytical chromatography. Again, you can see these beautiful peak shapes. They're narrow, they're sharp, they're well resolved, meaning they're spatially separated from each other. There's gaps between CBD, THC, and CBC, for example. So here is an example of preparatory chromatography, where we're not at all interested in the beauty of the peaks. We're interested in what kind of throughput can we get onto this system, but yet still get the kind of separation we want. And so when we talk about supercritical fluid chromatography, we're often talking about what cuts we're making. And it's just basically a cut is, when are we sending material to a specific separator? So for example, in this image, you see these three boxes colored red, green, and yellow. And you can see, for example, that the red box is essentially outlining the CBD peak between 9 and 11 minutes. So that x-axis is minutes. So between 9 and 11 minutes, we are collecting CBD into one of those separators. Now you could see that there's not baseline resolution, meaning that, where the THC peak and the CBD peak meet, for example, is not at the baseline being defined like you see from, 0 to almost 4 minutes. That would be considered our baseline. So this isn't quite baseline resolved, and that means there's likely going to be some bleed through of THC into that CBD fraction. Likewise, you see that the green and yellow box are kind of going into the peak labeled as CBC. So we would expect there to be some CBC in the THC box as well, in that fraction. So what that means is, we can tune our system based around this. We can change these cuts effectively if we're getting too much of a specific cannabinoid in a cut where we don't want it to be. For example, if we're trying to remediate THC, we can change the cut and make the CBD cut a bit more narrow. Maybe we take it all the way down to 10.5 minutes instead of almost 11 minutes, and we can effectively get more THC out of that fraction, but also perhaps at the expense of a little bit of CBD. So there's definitely some trade-offs here. But I think the take-home message is that we can tune this effectively. And then let's say we do have a little bit too much THC in our first fraction. We can then rerun that first fraction and try to clean that up a little bit more. So the purpose behind this slide is to show that we do stacked injections. This is to maximize our throughput. But the importance of it here is that when you look at these peak shapes, it's very important to note that they are not changing by much at all, if at any. And so this shows the repeatability of injection upon injection. And that's an important factor when you're evaluating whether to invest in this kind of technology, because if it was not repeatable, you would have to have somebody watching over this all the time, which is an expense to sit somebody there and park them there to babysit the machinery. This shows you that you can get repeatable injections. So this is over 7 injections where they were very repeatable from one injection to another. So, we had that initial sample. You see it again here. We basically ran this product through the SFC system, and we were able to take out the THC. You can see it's maybe a faint blip there, but the importance is we're trying to get it either to compliance for our customers or to non-detectable levels, however that is defined by their third-party lab of choice. So you can see that we were able to recombine fractions such that you still have minors like CBC, you've got your CBD, there's just not THC in the product, or if there is, it's at compliant levels. So here's the numbers on some of these fractions that we got individually, but prior to combining them. So you can see F1 was as expected, predominantly CBD. That's what we were targeting. Definitely compliant levels of THC. That level of THC is right around our limit of detection internally with our analytics. Some labs only report down to 0.1%. So anything below 0.1% would be considered non-detectable. So, this did that quite well. F2 had higher levels of THC, but this shows that we were able to effectively remediate that. There was some CBD loss there, again, because of that overlap. So you see this tested at 40%. And with F3, we see the minor cannabinoids are much higher in proportion as we would have expected. So, you might see this and say, well, there's 40% CBD lost in F2 and 14% lost in F3. The real question is, what are the masses of those fractions? So you can see specifically where the CBD went by by mass across all of these different fractions. So here is the mass balance. So we started with about 780 grams of material. We effectively recaptured 778 grams of material. So there really were minimal losses in the system. We were able to get about 87% of the CBD. So this is not a potency. This is saying if we start with 100% CBD, where does it all go? How does it get divided? Well, 87.2% was in fraction 1. Fraction 2 had a little bit less than 9%. Fraction 3 had less than 1% of the total CBD. And so you can see, like I had mentioned on a few slides ago, that we had combined F1, F3, and F4. So when we combine those three fractions, we have over 91, almost 92% of the total CBD accounted for. So just to point out a few of these particulars on the left-hand side too, we are using ethanol as a co-solvent, but very minimal amounts. And the throughput of this under these conditions was about 2.2 kgs per day. With the SFC60, our higher throughput system, again, I wanted to show that the sense of repeatability from injection to injection. So this is a high throughput system. And in order to maximize that throughput, again, if you have to have somebody sitting there babysitting it, this could be very time consuming and costly for you. So the fact that you can get repeatable injections means that you don't have to park somebody there. You could have them viewing this remotely with something like TeamViewer so that they could monitor things in real time, but not have to necessarily be dedicated to this system. It can run automatically. So that's a nice benefit. And again, with the SFC60, we were able to run material through there. We achieved an 85% CBD cut. THC was about 0.14%, so about half of what's necessary to be at compliance at 0.3. And so, this shows you how, depending on, what the end game was, we could either reprocess this, try to strip out that remaining THC, or we could leave it as is. And if we're doing downstream formulations and dilutions, we can get this product to an even lower THC value, such that there's no ambiguity with compliance. One last time, just to really hit this home, the ideal scenario is that you can Ronpo peel this thing and you can set it and forget it. And this is hundreds of injections, not just 7 or so like I showed on a previous slide. The idea is that you can set this up for hundreds or thousands of injections and not have to worry about the chromatography changing. If the peaks are changing and you're trying to send, especially if the elution time is changing, even subtly, your cuts can be greatly disturbed. And so it's highly important that the chromatography is repeatable. And that's what this slide is revealing. So we've also used SFC for pesticide remediation. And so we spiked a CBD oil with 7 pesticides, widely known pesticides and commonly used in California. You can see those pesticides on the left-hand side. You can see the levels that we spiked to on the right-hand side. And so it was the same challenge. We want to purposely contaminate this matrix, and then we want to try to pluck CBD out of that matrix, leaving all the contamination behind. And so you see our cut on the SFC on the left-hand side shaded in green. You can see some other peaks there. We were not interested in those. We were just trying to capture CBD here. And on the right-hand side, you can see that we were using UPLC to evaluate how much CBD was there, and you can see a very clean chromatogram showing that it was just CBD that was in that fraction as per UPLC. But we also needed to turn to mass spectrometry to evaluate the levels of any pesticides still in that CBD-rich fraction now. So we used mass spectrometry. You can see these total ion chromatograms here that kind of show us the spectra or the chromatography, the retention time rather, of these different pesticides. And so this table just kind of summarizes the entire experiment. On the, you see the California limits, you see what we spiked it to, and you see what we quantified in our CBD fraction. So some pesticides like permethrin, we did not detect any, we basically did not pull any of it. We did not leave any of it behind, rather. We pulled all of it with us. So we started with 360 parts per billion. We ended with 360 parts per billion, but that spike level happened to be below the California limitations. Other pesticides, we were able to reduce by several orders of, by several, 5-fold, 10-fold, something like that. So we were able to clean this fraction up so that this CBD-rich fraction would now pass California regulations. Another application is to be able to salvage cannabinoid losses from mother liquor created in the process of CBD crystallization, or thereby creating CBD isolate. So this is kind of an example of a garbage to gold opportunity with SFC. And so I'm sure everybody in this crowd is familiar with crystallization and CBD isolate. Just to kind of quickly summarize here, this type of process uses organic solvents, could be hexane or pentane or something like that. And you're using it to essentially get rid of everything else but the CBD. So the CBD becomes an isolated powder. This creates a large amount of waste solvent, and you can lose a substantial amount of CBD, not just CBD, but other cannabinoids in the waste solvent. But this is, a very common and cheap form of isolation. A lot of people turn to this because of those factors. It is a cheap way to go about doing things. However, because you're working with solvents that could be toxic, they can be carcinogenic, you may have some problems getting this certified downstream if you're looking for organic certification or GMP certification. So you could either isolate those cannabinoids using SFC by itself, or you could clean up the mother liquor by using SFC on that mother liquor. And so, this is a process that can be certified CGMP and can be certified organic if all of the other steps in your process are also certified organic. Yes, this does require specific expertise to execute, at scale. However, I showed you this repeatability, so, you might need somebody, a specific expertise to get the method off the ground, but then you can, again, Ron-po peel this thing and set it and forget it. Okay, so this is an example of the mother liquor that we worked with. So you can see this is about 40% CBD. So, again, I don't have the mass of this material listed here. That's definitely an important factor in determining how much CBD loss you actually had. But you can see there's a lot of cannabinoids in here, and we can try to get out the bulk of the CBD or the CBC, for example. So this chromatogram here shows you our cuts. We were not interested in the THC peak that you see eluding at around 6.8 minutes. So the first cut is trying to focus on CBD. The cut shaded in yellow is trying to focus on CBC. And then there's other minor cannabinoids in the final far right cut that you see here. And here's our analytics. Fraction 1 was predominantly CBD as expected. Fraction 2 was predominantly CBC, and fraction 3 was CBC and some CBN and CBG. So this shows that SFC is a valuable option for recovering greater value out of things like a mother liquor. So I mentioned that you can use SFC to target the individual cannabinoids themselves to isolate them, such as cannabichromene. And none of these processes are without having to do some method development. And I just wanted to show a quick example of method development. So you can see this, what I'm calling a narrow cut on the left-hand side. And the middle graphic on the bottom row of images here shows you that cut. So it is the cut boxed with red, so you can see that red box kind of going up the center of the peak, not quite trying to capture the entire peak. And we were able to get about 67% CBC with that cut. But because this technique is so tunable, we can then either just re-purify that, we can change our cuts a little bit and try to get a higher percentage of CBC. We did that, we were able to increase up to 83.5%. So this just kind of shows you an example of, doing some of that method development along the way to getting a high potency minor cannabinoid. So that's about it for what I wanted to share with you regarding CO2. I just wanted to quickly summarize some of what we've discussed herein. So, CO2 is generated from processes, but can be captured for further use. Many different botanicals are already extracted with supercritical CO2, and you can check out the scientific literature. I like to start with Jerry King because he's got a lot of nice literature on different applications of CO2 extraction and purification in general, well outside of the cannabis industry as well. And the scientific literature is definitely rife with that type of interest because many people are trying to supplant their uses of organic solvents with something a little bit more eco-friendly. We use supercritical CO2 analytically, where it replaces solvents like methanol and acetonitrile. And again, you can use supercritical CO2 for preparatory chromatography to isolate and purify molecules of interest to you. So regardless of whether you're creating high potency cannabis concentrates, whether you're using something like subcritical CO2, which we did not talk about, to capture terpenes in your biomass prior to moving on to the more resilient cannabinoids, if you're trying to extract essential oils like this lavender oil, if you're trying to separate mirror image molecules from each other, or if you're trying to create a really cool beer using supercritical CO2 extracted hops, or if you're trying to decaf coffee or tea, supercritical CO2 and CO2 in general can be recaptured and put to greater good for these processes. With that, I thank you for your attention, and I look forward to chatting with you more in our live Q&A session coming up next.